Still, good morning. Welcome back. Right, we are resuming with our program, going to the second half of the program schedule itself. So at this particular juncture, allow me to call upon our next speaker, the session. Just a moment. I hope I'm not butchering your name. It's Miss Raisafe Sefala. Oh, the first one, I know I didn't get that right. Please correct me.
It's Raiseje.
Raiseje. Okay, thank you very much for gracing us with your presence, and we are looking forward to your presentation. Let me see if I can share the screen just to show you the attendance or people that are waiting to hear from you from this end. Just a moment. Okay. It's a bit slow, but we should be able to show you from this side that you have almost like, it's almost a full house actually that is waiting for you. I'm not going to take a lot of time, maybe jumping into the introductions. What I'm going to maybe ask you to do from your end is maybe just do your quick introduction as we jump into your presentation. Maybe whilst I'm trying to sort out my take here, you can check if you're having any presentation, if you're able to do the sharing, then you can jump into your introduction. There you are. So you have that full house waiting for you.
Oh, thank you. Thank you everyone for coming. My name is Raiseje Sefala, and I am a research fellow at the Distributed AI Research Institute. So in today's talk, I'll be going into how else, like more creative ways we can think about creating ground truth data sets to answer research questions. Okay, maybe I should also share the slides to just give you a little bit about the kind of work I do as well. Okay. So these are some of the organizations I've also contributed to. I do a lot of work in mostly applying AI techniques to looking into, like, exploring ways in which we can apply AI techniques to real world problems. However, the biggest challenge is always curating good data sets so that our models can actually learn from like the data that we have and give us outcomes that we honestly expect. So I do a lot of sort of satellite imagery work together with other data sets and working with other domain experts to try explore solving problems that are experienced by societies like the ones that I live in. So we're machine learning researchers, and as such, we always want to use our skills to solve impactful real world problems, especially those in developing countries where there's a lack of resources, the shortage of finances. We want to find creative ways in which we can use machine learning to firstly understand the kind of landscape, see if we can actually read it and understand it for the way it is, and see how we can evaluate how well our models work, and then apply them finally. However, the lack of ground truth labels is usually a big problem. So as researchers, we want to find ways in which we can actually suppress this and find answers to the research questions that we have. To just give you some perspective, ground truth is the reality that you want your model to be able to predict. So when you're building a machine learning algorithm, you want your model to actually be able to relate the data that it receives to the real world artifacts that they represent. So we do that using ground truth data. So to just give you some examples of what ground truth data sets look like, if you have a satellite image, for example, and you want to understand the neighborhoods in a satellite image, you would have an input image like this, and then you would have labels that show the model what to look for in an image that looks like this. So the labels could be different, showing different perspectives. However, for a particular outcome, you need to know what your labels should sort of look like. So if you have medical imaging, for example, you would want to show your models where the heart is, where the liver, where the kidney is, so that it can actually learn from seeing what the labels should look like. And then in an unseen image, it can actually identify those objects. But the problem or the challenge with getting these ground truth labels that enable our models to actually understand the real world is that curating these data sets is usually very labor intensive. I mean, machine learning models require hundreds of thousands, if not millions sometimes, to actually understand the problem that you're trying to give it. So if you have medical imaging, for example, you will need like a lot of these examples, a lot of these complex examples as well, so that it can learn. But coordinating, getting those hundreds of thousands of images, for example, is very labor intensive. You have to find people who are going to label each and every pixel, for example, in this case. And they have to label hundreds of thousands of these. So you have to get a group of people who can do this if you're trying to reduce the time it takes. And if you have a group of people, it usually is financially expensive, because sometimes these labels are not labeled by ordinary people. Like maybe you need a domain expert to actually tell you if a heart has a defect or there's something wrong with XYZ. And this could be quickly financially expensive. And sometimes you have things like satellite images where you take pictures today, maybe this neighborhood doesn't exist at all. 2 weeks later, the buildings are there, or like a month or a year later, there are a lot more buildings, and the images that you took last year become quickly invalid. So you'll need to regularly update these, and updating them means you need to always have a group of people who are labeling all these. And if you have a group of people as well, they have to, their labels have to agree with each other. So if one person sees a person here, the other person who's labeling must see a person like the same way the other person is seeing, so that the labels can be coherent. So these are some of the challenges as to why we can't usually have ground truth data sets or labels that are up to date that we can use for our machine learning models. So the big questions are, can we generate, in trying to suppress this, can we generate labels using existing algorithms? And another thing I'll be touching on is, can we create relevant labels from pre-existing ground truth data that was labeled for some other task, but then use it or change the labels in such a way that we can actually use them for a different task. So I'll start with this project that we did. So given traffic footage like this, can we actually identify what's going on here so that we can help improve traffic safety in scenes like this? I mean, if you can see that it's a one-way road going that way, but then you can see there are some dangerous things that are happening in scenes like these, where you get people going the wrong way and things like that. So how can we improve traffic safety in scenes like this? So we didn't have labels for that project. And the big question was, can we actually generate labels using existing algorithms so that we can identify things like that? So this was a project that we did for Data Science for Social Good Fellowship. together with my team in partnership with Jakarta Smart City and Pulse Lab Jakarta. The project was based in Jakarta, and the government wanted to improve traffic safety in the city. However, they didn't have labels. They just had thousands and thousands of hours of footage like that one, but then they didn't have labels for them. So we wanted to understand if we can extract data from these videos that we are seeing to inform possible interventions in order to improve traffic safety in the city. So for this project, the context was that Jakarta was a city in transition. Since the 1970s, it has just been rapidly growing. Like there was a lot of urbanization happening in the area, and the government had not planned for so many people to occupy the city. So there was like a very terrible traffic problem because people wanted to go to work in the morning. In the afternoon, they wanted to come back from home or pick their kids from school or other things. And then that just caused a lot of congestion in the roads, causing a lot of traffic safety issues. And in a typical day in Jakarta, you could see something like this, where everyone is trying to get somewhere and there's just no order. I mean, look at this person who is riding a bike, a motorbike. They have like a pile of boxes. They can't even see what's going on at the back. But then they're also navigating. There is food carts, there is pedestrians, there is cars. There's just a lot of chaos. And this causes a lot of traffic safety issues for the people who live here. So the government wanted to identify all these traffic risks and find out at what time they're happening and how frequently they're happening. But then so that they can identify these and then help, like, you know, find more medium to long-term ways to intervene. So they were looking for things like people who are driving the wrong way, people who are parking illegally, those stopping at forbidden stops, street vendors on the sidewalk. This was actually a big problem, the street vendors on the sidewalk, because this will force the pedestrians to be on the road, and that was causing more traffic safety issues. So the kinds of interventions that we're looking into were how to like, you know, where to strategically place signal, like traffic lights, where to deploy traffic. There are limited resources of traffic officers in specific places at specific times, or where to do like more long-term things, like where to put barricades or change the way the road looks or expand the road and things like that, and how they can better plan for public transport. So what they had was over 7,000 actually CCTV cameras all over the city. They didn't own all of these CCTV cameras. Some were owned by private institutes like the banks and other places like that, but the government had access to these cameras. So their current methods of data extraction were they had a person looking at these cameras and noting 3:44 p.m. there is XYZ happening at this intersection. And then they had to look at these cameras and then note all these and extract all this information. But now they had over 5,000 cameras, and then scaling just didn't make sense because there were more videos, and then this was happening throughout the entire day. So they couldn't actually scale the number of people, which is why they thought maybe using machine learning would be a better intervention. So instead of having people, they could have like a machine learning model that actually helps to extract this data set. So this was our solution. We were thinking of, given a traffic footage like this, can we firstly identify all the objects? Can we identify if these objects are moving or not? And can we also identify where these objects are moving? Are they moving on the road? Are they moving on the left side of the road or the right side of the road? Or are they moving on the sidewalk? And things like that, so that we can identify things like motorcycles moving the wrong way on the road, or pedestrians on the road at a particular spot, so that in interventions, evidence can be gathered up so that they can intervene properly. So to do the object detection part, we used YOLO. So at the time, YOLO was very convenient because it was super fast and it was more accurate than the other models. So how YOLO works is that it looks at an image at different scenes. So if you can imagine, a video is just a set of images captured at different times. So put together, they create this motion picture. So YOLO looks at individual frames, and then it looks at them at different scales, and then tries to create bounding boxes. And within each bounding box, it predicts what the object could be. And then it then looks at the most likely outcome and then gives you that prediction. But it looks at it at 3 different scales so that it can give you a more accurate picture. So yeah, so YOLO worked really well. However, so YOLO worked really well. However, the problem with this particular model that we had was that it was trained on the COCO dataset, and the COCO dataset was trained on images from more developed countries like Germany and other places like that, where things like things like tuk-tuks and minibus taxis do not actually appear on the roads. So we had a lot of errors in trying to classify those. But on how we actually tried to solve that was that we coordinated labeling of a few frames, and then we fine-tuned the model to actually be able to also identify these motorcycles. But before, you would get things like a tuk-tuk being mostly identified as a bicycle, or a food cart being mostly identified as a train sometimes. So which is why we needed to actually hand label these and then fine-tune these models. For the motion detection part, we used the Lucas-Kennard optical flow model. So here, it looked at a couple of frames and then looked at the rate of change of these objects that we would have identified using YOLO. And then now we were able to say a car is moving in a particular direction, given the orientation and the perspective. So we were able to find cars moving, motorcycles, like all these objects that we identify, we were able to see if they're moving or not, given a couple of frames. The problem with Lucas-Kennard would be that it wouldn't work so well with cars that are moving super fast, but because of the traffic congestion problem in Jakarta, the cars were not moving so fast. Like the objects of the vehicles were not really moving so fast in these scenes because of the traffic jams. So it worked really well for us. We also used a semantic segmentation model to try identify where these objects are moving in the scene. So here, this is quite an expensive process computationally, but we didn't have to do it so often because the cameras are stationary, and then now we could do it at maybe early hours of the morning, and then we would capture the road when it's almost empty so that we can find where the position of the sidewalks are, the roads, and things like that. So this actually worked out really well for us. So just to sum up the pipeline, we read images into the pipeline, and then we moved on to the object detection part, and then we stored the coordinates of the object and the names of the objects. We moved to the motion detection part, and then we stored, for the objects that we identified, are they moving or not? And then we stored that information. And then we moved on to understanding where these objects are moving or not. So that at the end of the day, we can actually say a motorcycle is moving left on the sidewalk. But then we would have other metadata to say what left means or right means in this case, or a car has stopped on the road. And then we would be able to flag these so that maybe at the end of the month, we could say, on this particular intersection, there were 50 motorcycles that were moving the wrong way, or there were 10 cars, or maybe 200 cars that had stopped at around this time, so that now the government can say, okay, there's enough evidence for us to actually intervene and put a traffic officer at this point at this time, because cars like to stop at this time, and then they can actually help with the traffic flow and other interventions like that. So that worked relatively well. And in the second project that I'd like to highlight, we wanted to see if we can actually adapt relevant labels from other data sets that were created for other tasks and see if they can actually work for our tasks, because creating data sets is quite expensive. So for the second project, we wanted to classify residential neighborhoods according to their types in South Africa. However, we didn't have ground truth data. So we wanted to see if we can put together different data sets to give us the answers that we think we need. So to just give you some brief, this was a project that I did as part of my master's degree. We went on to actually publish a paper and a data set for this work. So here we were trying to use satellite images and computer vision to study the evolution and effects of apartheid in South Africa. To just give you some context, so during apartheid, there was the Special Apartheid Act. So what that act meant was that it forced like all the non-white races, people that were living in South Africa, out of their suburban homes, people who owned homes in the farms, in the suburbs, everywhere in urban areas. It just moved, this law or this act forced them to move out of their homes into neighborhoods called townships if they're not moving back to the villages. And in a township, this is what a township looks like. So in a zoomed in level, it's like, they look like this. So they try to sort of squeeze a lot of people in a very small space. So the houses were uniformly sized, more or less, and then regardless of the number of people who are living in the house, they were like uniformly sized. If there were 10 people, 5 people, the government didn't really care. But then each home had a had a family. And in each neighborhood, in each township neighborhood, even though there were a lot of people living in the neighborhood, they had like hospitals and schools that were underfunded, proportionally, like as proportional to the number of people who are living there. So they were overcrowded, the resources were underfunded. The picture that this GIF here in the middle, the beige part, this is actually a township called Tembisa from 1984 all the way to 2019, I think. So I'm just trying to show how consistently this neighborhood has been growing. Like it still looks the same. Even today, if you look at it on the map, the neighborhood still looks quite consistent. And it looks really different from the suburbs that are next to it. So even past apartheid, like apartheid has ended in South Africa, the neighborhood still grows consistently. And we still see these hospitals and these schools in these neighborhoods are still being overcrowded and underfunded. So we're just asking ourselves, although apartheid has ended, why are the neighborhoods not changing? Because before we knew that it was because of apartheid, but now how do we hold our government, our current government, accountable for these neighborhoods still being marginalized and underserved? So just to give you more of the context, this is what a township looks like. This is Cape Town in South Africa. This is a township next to a suburb. And here is a suburb next to an informal settlement in the image below. So the legacy of apartheid still exists even today, but then we wanted to actually quantify how much, like why, like we wanted to understand why. Firstly, we wanted to gather evidence as to that the neighborhoods in townships are not changing. The conditions in townships are not changing. But then the problem with this was that we didn't have ground truth data to show us where all these townships are. But if you look at the satellite images, like technically, we can actually see that we can actually identify townships from these visual representations. So we thought this was a good computer vision case, and then we went on this quest to demarcate the extent of these township neighborhoods. But we did it for all the neighborhood types so that we can, at the end, say this particular one is a suburb, that one is a township. Even on years post when our labels were created, we can still say in 2025, this is what a township looks like, or this is a township, and this is a suburb, and things like that. So for that, for that problem, the only data sets that were available for us were data sets from 2011, and it was satellite images of the entire South African country. We also had this data set that showed us where all the buildings were. So each point denotes a building. So just to give you some context, this is the same township that I showed you, Tembisa, and next to it is a very wealthy neighborhood. So this is the density of, this is the density of buildings in Tembisa. It just shows that in a township, there are a lot more buildings compared to suburbs or like wealthier neighborhoods. And they still grow consistently. In townships, people still get very small pieces of land, despite the fact that over 90% or like over 85% of the country is non-built up, it's vacant. But, you know, still from apartheid, people who choose to build houses in townships, they still get land sizes that are very small, that are comparative to those during apartheid. And the one data set that we had as well from the government was this data set that showed us what the land is supposed to be used for from the census of 2011. So the problem with this data set was that the townships were not labeled. So townships from after apartheid, townships have been merged with suburbs so that they're called formal residential areas. And now if you're looking for townships, you can't really find them. But what we did in this work was that we looked at the entire country and we coordinated a labeling task to label all the townships in the country so that we can actually be able to identify which land was used for townships. And then we disentangled the townships from the suburbs because we wanted to be able to track the townships going forward. We don't know why the government merged suburbs and townships, but this merging of it made it very impossible for us to be able to track the growth or the changes in the township, which is why we had to go on this labeling quest. So how we did our final data set, we used the satellite images that we had and we overlaid them with the building data set that we had. So each point here denotes a building. So because we wanted to use computer vision techniques, we had to change these points into polygons. So this point here will show you that there's a house here. So what we did was to look at like an average South African house, and then we changed these points into polygons that cover more or less an average South African house. So after doing this, we overlaid the points and the polygon. We got an intersection of the polygons and what the land is supposed to be used for, so that we can say these buildings in red form part of a village, and then the ones in green form part of a farm, so on and so on. So after that, because there was like 12 million buildings in the country in 2011, we didn't want that computation cost attached with like looking at 12 million sort of labels per image, like per country. So what we did was to dissolve these polygons into one, because what really mattered was the neighborhood itself and not so much the individual households. So we dissolved all these polygons into like 12 big polygons denoting our 12 labels. And then we did this for the entire country so that at the end we have something that looks like this. So you have given your satellite image, the labels will look like this. So the yellow will show you where the townships are, the red will show you where the informal settlements are, the blue show where the suburbs are, and so on and so on. And the white shows you the background. So given an image like this, it was not even an easy task. Like, we started off with image like this and the labels from the government. And then we realized that training a machine learning model with labels that look like this, this is what the land is supposed to be used for. It doesn't tell you that the land has been developed on or what. So we started off, the first iteration started off with us using these labels. When we trained our models, the model would get it super wrong, especially on the vacant parts, because we're saying this land is supposed to be used, it's supposed to be labeled as a suburb, for example. But then when the model looks at this part that is vacant, there's nothing about this visual characteristic that tells you this land belongs to suburb. So that was why our model was getting it wrong here. So we had to iterate, look for another data set. And we found this data set that shows you, like, these are the real estate, shows you individual real estate ownership. So this is land bought as denoted in the government registry. However, it shows you that this land was bought, but it doesn't tell you whether it was developed or not. So this still gave us the same errors. And another problem with this data set was that land in informal settlements was not properly recorded, land in villages was not properly recorded, and places like that. So we were missing some labels in some key classes, but then this data set could not be able to satisfy that. So this final data set that we had just created defines neighborhoods in terms of the presence of buildings. So what that means is that where there's a building, we have like the labels cover that part. So where there are no buildings, although the land is supposed to be used for X, it doesn't actually cover it. So we can still define neighborhoods in terms of visual characteristics of the buildings. And then this is why this data set worked. So for the segmentation part, we used a UNet. We also used a deep lab semantic segmentation model. So how these models usually work is that they take in as input an image, and then they look at the entire image in different sections, like segments, until they give you a label per pixel. So they label each and every pixel accordingly. So the nice thing about, because neighborhoods are very regular, we can, if we're labeling each and every pixel, we're able to actually get better labels than saying this whole image is XYZ, or a bounding box shows a township, or something like that. I mean, given that an image like this could contain a suburb here and then a township this side, labeling each and every pixel works out really well rather than labeling each and every image. So given our actual images and ground truth that looks like this, our models were actually giving us really nice results. So state of the art at the time, on 10 classes of a similar task, that was the mean intersection of a union was 54.96, and our mean intersection of a union over 12 classes gave us 45.85, which was really competitive to the state of the art. So we explored other things, like we had 12 classes, and then we moved on to dissolving those 12 classes into 4, so that we can understand where wealthy neighborhoods were, non-wealthy neighborhoods, non-residential neighborhoods, and the background class. And looking at those kinds of results over the 12 provinces that we had, we were able to get better results. And the other reason why we dissolved the classes was because townships were being confused with informal settlements and sometimes villages. And these are like within the same sort of socioeconomic status. So which is why we decided to look at the value of the housing in townships sort of informal settlements and other places like that, and then lump those together. More wealthy neighborhoods according to the value of the houses, and then lump those together as well. So that's how we came up with these 4 labels. And then we were able to explore what our models see in different in different provinces. Another problem with these models was that, given ground truth like this, some models were more sensitive to some parts, like the food parts. The deep lab model was more sensitive to food parts. So given a food path, because in a lot of these images that it sees, a food path indicates that there's a house somewhere. So it would be more sensitive to getting that false positive. Sometimes they would also look at like parts of a mountain like this. This might be something that looks like some part of the land, or like, some neighborhoods would have this sort of characteristic. And then the deep lab model was more sensitive to false positives like that. And if you look at it, the deep lab model was much better on other tasks, generally, for other papers that were published than the UNet. But in this case, the UNet worked a lot better for us because it was not that sensitive to these false positives. So looking at the 12 classes, sometimes we would have suburbs that look like this, and it would classify them as a village. Our model would classify them as a village. Sometimes we'd have suburbs that look like that, and then our models would misidentify them as townships, and so on and so on. And the reason as to problems like these is that, we were looking at the entire country. So suburbs in different provinces look different. Looking at these suburbs, for example, everything enclosed in this blue boundary is supposed to be of a suburb. So some suburbs have smaller pieces of land, and others have more massive pieces of land. So when you're trying to create labels like these, you must take that in mind, that the entire country is not uniform. So you need to find ways in which you can try to understand what the landscape sort of looks like and what it means, and what kind of labels actually work for which landscape. So these are all wealthy sort of neighborhoods, but then they are wealthy in different subcategories. So these are all suburbs, which is one of the reasons why we collapsed the classes from 12 classes to more like 4 classes, so that we can actually identify a wealthy neighborhood versus a non-wealthy neighborhood, instead of like a suburb, a small holding, when they're both wealthy neighborhoods, or like in informal settlement and a township, and so on and so on. So given an image from 2011, that looks like this, where there are just a few buildings in 2011. Our model was able to look at be trained on this data set on the first row, and then to predict what the kind of growth that's been happening in 2017, for example. So this is the same image. This is the image of the same place. So in 2011, there were not a lot of houses, but our model was able to actually pick up that more houses were being built. So thinking about a problem like this, if this was a township, for example, in 2011, we're able to pick up that there was growth of this township, and then overlaying other data sets like hospital data and school data, we are able to ask questions like, given that we can see that there is growth in this neighborhood, how have the number of beds in the hospital been changed? Has the hospital been upgraded, or are there more schools in the neighborhood to actually cater for this capacity of buildings? And then looking at this and then more wealthy neighborhoods, is there a disparity in the rate of growth in the two neighborhoods, given that we're in a democratic country? So we're able to actually ask these questions given these indicators. And also we're able to look at the land, the development of the land. So given that in 2011, the background or the non-built up part was this much. In 2017, this is how much it has actually changed. So we can see that in Gauteng, for example, more wealthy neighborhoods were built where there was no buildings before, rather than non-wealthy neighborhoods. And look at like things like that. So thinking about changes as well, like the detecting of the changes that I was talking about, given land that was vacant in 2011, what kind of growth has been happening? Because we can see that in 2011 here, this is part of Soweto. It was like this, and then now it's been growing, it's been changing. So can we actually use our models to actually detect change like this? So some key takeaways from doing these two projects was that thorough evaluation was very key in both projects. I mean, imagine we didn't have these labels before, and then now we had to find ways to actually understand how well our models are actually doing in the real world. The first project that we had, I think I was like the only person from a developing country. So when we had to decide whether or not the models were doing well, they were doing very terribly on minibus taxis. So a lot of the people in the team were like, maybe we can just ignore, or we can accept the error on minibus taxis. And I was able to actually say, actually, no, we can't do that, because minibus taxis form a very key, like a very significant role in developing countries. So we actually need to create extra data sets for that. Also in the second data set, where we had to identify things like townships and all, because I come from a township, I knew when the model was not doing right. So I had to look at a lot of things, a lot of indicators that were able to actually give me like, signs of that the project was not going as well as we were thinking. I mean, given that we wanted to look at the evolution of spatial apartheid, townships were quite key. So I knew how that was important, and I knew when the models were not doing well. The project took us like about 4 years to complete, but then that 4 years was because of the thorough evaluation. I mean, the model was not doing well, and we had to just iterate and iterate until we got it right. So, which brings me to the second point, that this is usually a very iterative process, and it takes time. Like I said, the other project took us like about 4 years to complete, and it's okay because we wanted to do a thorough process, a thorough sort of a thing for this project, because it's really important that we actually capture the perspective that is the reality. Otherwise, why are we doing it if it's just for getting accurate models? So another thing is that you need to actually involve the main experts early on, because small technical mistakes will cost you a lot of time and resources. So there are people who've been looking at these things for a very long time, specific things really, for a very long time. So involving them in what you're thinking of doing is always amazing, because they will teach you a whole lot about this thing that they've been doing a long time. And finally, you should always understand that data exploration can be a little bit emotionally disturbing sometimes. There were times where I could see, like in 2011, there's like houses by like a riverbank. And then in 2015 or 2014, all those houses are all gone. Like you just ask yourself, what happened to the people who were actually living there, and things like that. So you should just take note that you are dealing with real data points. Like, these data points are real people, like literally real people. So you need to respect their data. You need to also respect their privacy. And if you don't need some labels, I mean, I could have used household level data, but because I knew that my outcome didn't require household level data, I looked at neighborhoods instead. So, and I created a buffer around the neighborhood, so it doesn't actually specifically find the neighborhood, but it just shows you where the neighborhood is, more or less. Thank you, and I will open up for questions.
Thank you, Mr. Fala. I hope you heard the applause. One thing that I can confirm for you, you managed to capture the attention of the audience from the beginning to the end. I had a silent room because they were following through the proceedings. Let's hear if there are questions from the audience. Anybody questions? I will also check online. Yes.
All right, thank you very much, Mr. Father. That was an in-depth sort of like presentation, and it was yeah, it was very much enlightening. One question I wanted to ask, though, maybe it'll be two, but the first one is like with the YOLO model that you're using. You said when you're explaining the pipeline, you said first you need to sort of like identify the objects, and then sort of like also identify like how fast they're moving and where they're going. And that tells you like where, for example, like when you've sort of like done everything, where you might need to place people who basically like be monitoring the road, or where you might need to make changes. But what I was wondering was, well, what about in cases of maybe bad weather, or like maybe it's like raining? How exactly do you combat sort of like identifying the cars and how they're coming in? And also like, well, what if they're carrying sort of like abnormal loads? Maybe they carry things that sort of like obscure them. So how do you sort of like, well, tinker with the model? How do you deal with actually identifying those objects?
Yes, so for cases of like bad weather and other things like power outages, causing corruptions, actually, those were like things that were literally happening. So when we were still fine-tuning the models, the data that we were using was not so much focusing on like bad weather and things like that. But then we didn't just look at like, you know, the videos, just the videos. We also looked at like weather predictions as well. And we would attach that there was bad weather on this day. So whoever is going to be collating the final the sort of results, they would take into account that this one maybe was not so accurate because of the weather and things like that. I mean, depending on what they value, they had an option to discard those results or not count them. But when we were fine-tuning the models, we picked specific parts of the footage where there was no corruption, where there was good weather, but then not like bright weather always, but then sometimes it was raining, sometimes it was a little bit dark, sometimes it was very bright and sunny. And then we tried to also incorporate those sort of variations in our fine-tuning.
Any other burning question? We may have maybe time for two.
Well, thank you very much for your presentation, Mr. Fala. Wow, as you were talking, I was basically just nodding to your presentation the whole time, like I was sort of following as you speak, basically. However, I have two questions here. I just wanted to find out, I don't know if I count who are followed very well, that you showed us about 2 to 3 things, if not 15, sorry. But in terms of the first project that you showed us, I think you said it was Gemini. So I wanted to understand, how did you guys come up, since that you said you used the similar software or probably to detect certain like vehicles from the European countries. I just wanted to find out, how did you guys come up to identify and label the rest of the items that I know must have been a million that does not actually have any African countries, such as the motorcycling and some other things on the road? And how did you guys come up with that labeling? And did you guys get to run the test run? And how did that work, basically? The second question is, when you speak of land survey that you guys had to do, did you guys compensate on the deviation of GPS? Because I know you basically said that what you guys had to do is
the compensation of the did you say DBS?
Yeah, the deviation of the GPS, sort of the location. It doesn't basically just show you the exact location. It will show you off like maybe 32 meters offline or something like that. Or did you just use what you guys had?
Okay. So for the first one, for your first question, thank you for the questions. For your first one, I literally was given a TV and I looked at, I think, like thousands and thousands of hours of footage, like I think for the first 2 weeks of the job, trying to just understand the like, you know, the objects in the scenes, and understanding the data set itself. There were like a lot of problems other than just the objects. I mean, there was a finite number of objects that were being seen, but then there were like other things that were happening in the data set that we couldn't have detected if only, like, you know, someone had sat down and actually watched all that footage. Like, you know, there was some corruptions. Sometimes in some places the power would go off, and when the power goes off, like it's like the footage gets corrupted because now there's no electricity. Or they're like, when the power comes back on, as it's trying to connect back to the internet, there would be like scratches that were happening. So if you would just run your model, everything would just look distorted. So we had to actually sit down and watch like all those hours and hours of footage so that we can identify those. But then for the second question that you asked, the data sets that we used, especially the building data set, was very specific. Like it was on point, finding the center of each and every building. So it was created in a very expensive manner. It was not even our data set. It was a data set by the Power Utility Company of South Africa. They use that data set to plan. So given the number of buildings in the country, they could project how many more buildings could be built so that they can plan for how much to spend on like transformers or like connecting them to electricity grids. So the data has to be very accurate in finding exactly the buildings, all of the buildings. So yeah, so that was, yeah, the nice thing about it was not just a survey, it was like an exact, that was ground truth, like real data, like all those buildings existed. So yeah, that's for the second question.
Thank you, Mr. Fala. I'm just checking our time and I'm very much worried. Can I ask maybe the other burning questions that are there to be posted on the chat? Maybe you could also respond via the chat. As we can also see from the chat, there's already an appreciation from the online audience to say we appreciate for the outstanding presentation. Keep the great work up. I'm just checking our time, so I may have to cut the questions from here, but just expect some questions in the chat. And I hope this is not the first time we are going to engage with you. Thank you very much for really being part of this Indaba X for Namibia. And we're looking forward to engaging with you on other platforms as well, and even further collaboration. Once again, thank you on behalf of the team here.
Thank you.
Right, as we move on with the program, I just want to confirm if Mr. Robert John, you're online and you can hear us, and you can maybe also check if you're able to share your screen if you have your presentation.
Yes, I am online and I will try to share my presentation. Good afternoon, Namibia.
Good afternoon. Right, I'm not going to do any more formalities because we are already on the top of the hour, which is at 12 sharp. This is already a minute past. So I'll simply say, maybe just take this opportunity to just quickly introduce yourself and jump right into your presentation. Thank you very much.
Okay, thank you. Unfortunately, Mark is doing something where I need to quit and rejoin. So just give me a minute, please, and I'll be right back.
Certainly, not a problem. And let's come back to the room. Indaba. This is not even impressive. Indaba. Much better. Right. Maybe whilst we are waiting for Mr. Robert to connect, I can take maybe one question. That was if it's Benny, that is. You had an opportunity.
All right. So looking at what Mr. Fala presented us, so one of the challenges on one of the projects they worked on was the data set. So I just wanted to ask, like, how does using a different data set from the location have an effect on the accuracy of the model?
Can you say that again?
Okay. I just want to find out, like, about the model you guys created in Jakarta, I think. The data set, right? The data set you used was, you said it was for another European company. I think, okay. So I just want to find out, like, how does using a different data set, with, according to the problem you're solving, that this data is totally not relevant to the location where you are. How does it affect, like, the accuracy of the model?
Oh, yeah. I mean, a lot of the problems is usually the objects that are in the scene. So, but then like objects like cars and like buses and motorbikes, bicycles, they were being identified with like a good accuracy, but then others were not. Also, the background sometimes was being identified as something else, which is why we had to sort of fine-tune the model with our data set, although we had this pre-trained model. So yeah, I think it's really important to actually adapt it in that way, because otherwise you'll get a lot of errors and a lot of things that you're picking up that are not even consistent if you don't do that.
Thank you, Mr. Fala. And Mr. John, I hope you are ready now. You can take the floor.
Yes, I am. Good afternoon, Namibia. It's a pleasure to be at this Indaba X. My name is Robert. And during the day, I manage a team of data scientists, data engineers, and machine learning engineers. And outside of work, I am an ARM innovator and a Google developer expert for machine learning and the GCP. And my topic for today is tiny machine learning. And tiny machine learning is machine learning on embedded devices. And when you think of embedded devices, particularly if you come from a software background, typically we talk machine learning, but it's usually on mainframes or on desktops. We don't really think about tiny computers that might be running ML models. But on the screen, I have, for example, a Google Home device, and that's a smart speaker. We see that in lots of places. We can wake these speakers up, when we use the wake word, that's what it's called. But I don't want to use the wake word because those things tend to wake things up all over the world. But you have these devices from Google, you have them from Amazon, you even have them from Apple. Now, when you use the wake word, these things sort of get activated and they start listening for the next set of commands that you're going to issue. And when you think about that, it is machine learning. And we have machine learning on lots and lots of embedded systems, whether they're using speech or whether they're using computer vision. So if you think of tiny cameras that you could have around the home that detect your pets or detect humans, or maybe even detect a baby crying if you have a baby monitor, those are all applications of machine learning. And that inference happens on device. It's not data that gets sent back across a network or processing. That's really the premise of tiny machine learning. Now, I'm going to go into a case study of this using something called Elephant Edge. And Elephant Edge is a project from Smart Parks, unaffiliated, but it's a very good case study for you to understand various applications of machine learning on embedded systems. So Smart Parks has taken upon itself the challenge of conserving wildlife. And when you think about the conservation of wildlife, particularly in Africa, what we're fighting is typically poaching, but then there could be other problems that we have to deal with. And so Smart Parks introduced what's called an open collar to help with that. But before we get to the open collar, let's look at how this was done in the past. So typically, if you had a conservation reserve or an area of land with wildlife and you wanted to keep an eye on what was going on there, you would make use of satellite imagery. And you could collect your satellite images and then run a model on them to do things like count the number of animals that you see and try to detect some sort of activity that is going on. Now, the disadvantage of using satellite imagery is that, first of all, it is expensive. It's not available to just anybody. But secondly, it's not real time. So you can't really tell what's going on at a very precise moment. You have to wait for the satellites to fly over that area, capture the images, and then send them back to you. Now, with edge devices, such as the open collar that we're talking about, you're able to implement a completely different paradigm. So first of all, those collars can have sensors on them. And there are lots and lots of sensors, but what you might be interested in could be things like cameras, microphones, and what we call inertial measurement units. And those are things like accelerometers that measure speed, gyroscopes that measure angular momentum, and magnetometers that measure the direction. You know, like it's a magnetic compass, essentially. Now, on top of these collars, you can also have communication devices. While we typically would think of communication in terms of things like Wi-Fi and Bluetooth, out in the wild, those aren't the most practical of solutions. So you would have either medium range or long range communication devices. And one requirement for operating out in the wild, but it's also popular with embedded systems, is a requirement for low power. So if you think about the cameras and the microphones, they are not the same ones that we have on laptops and desktops. They don't consume the same amount of power. And with the sensors and the communications in place, you're then able to do threat identification, because remember that we're talking about wildlife conservation. So you're able to do threat identification. For example, with the cameras, you're able to see what's around the elephants, and you're able to classify the images that are being captured. So do you have humans in the frame, or do you have something that is a natural predator for the wildlife, or are you just seeing other wildlife around? With the microphone, you're able to capture the sound that is in the environment. And so are you capturing sound from the animal itself? In the case of elephants, for example, what sort of calls are they making? Are they trumpeting, or are they just communicating between themselves? Or do you have sounds that are only produced when you have humans and poachers around? For example, do you have gunshot sounds that the microphone is capturing? With the IMU, you're able to detect the movement of the wildlife. So are they stationary? Are they sleeping? Are they running? Are they exhibiting some sort of aggressive behavior, or are they moving around like they feel threatened? So these are all things that a smart collar is able to do, and you can see right off the bat that this presents a completely different type of solution and capability as compared to satellite imagery. And this is what the open collar looks like. So it's a hardware device that you'll put around the animal. And on the next screen, you can see the capabilities that this hardware device has. And so further down, you can see things like a biosensor. So there's a heart rate sensor, and that way you're able to tell whether the animals have elevated heart rates, or whether they're even alive, right? If there's no heart rate at all, then the animal could be dead, for example. You have camera and acoustic sensors. If you go up a little bit, you'll see that the device has edge machine learning capabilities. You'll also see things like ultra high frequency and very high frequency connectivity, as well as 2G, 3G, and 4G connectivity, which is GSM connectivity. And things like solar charging. Now, when you talk about machine learning on edge devices, there's an intersection of various things. So these devices that we're talking about are from the world of electronics. Again, if you have a software background, electronics are not something that you might have encountered. They're probably not something that you think about on a daily basis. But when you look at the need, then you find that you can't provide this solution without electronics, right? I mean, even the models that run on phones, tablets, computers, they're running on hardware. But at the electronic level, you have a completely different type of problem. Programming electronics is not the same thing as programming desktops, general purpose computers. These are special purpose computers, usually single use. So if you think about the elephant collar, for instance, it's only suitable for the purpose that it was built for, which is wildlife conservation. It's really not useful for any other thing, like music identification, for example. So to do TinyML, you have an intersection of three things: machine learning, programming for electronic devices, as well as the electronic devices themselves. So the intersection of all of these is TinyML, or machine learning on embedded systems. Now, these electronics are called microcontrollers. They're special purpose computers. So while they're computers, they're not computers in the general sense that we think about. They have energy constraints. They use way less electricity. If you think about the collars, they're probably something that you want to put on the animal and then forget about for maybe the next 1 year or 6 months before you have to go and check for anything. If you look at that particular collar, it has capabilities for charging via solar. So that means that the batteries are rechargeable. And so if possible, you could let the animal go on for many years without having to interact with that animal. These devices are also memory constrained. So you can't deploy the traditional applications that you're used to. If you think of, let's even say, an Android device, when you build an application for Android on your laptop, how many megabytes are you transferring to a phone when you're going to do a deployment, or are you transferring to the Play Store? But when you talk about microcontrollers, that sort of memory is just not available. It's completely out of scope. And then even the processors, they're not the same processors that you have on computers, not the same processors that you have on phones. They're a completely different class of processors. So they're called microcontrollers. The speed at which they run is usually way less. It's usually below 100 megahertz, which is 1/10 of what you would get on your general purpose computer. These devices don't come with keyboards and mice, because who would put a keyboard and a mouse on something? They don't even have touch screens, right? Instead, they have input-output ports. These are just electronic ports. And so they get their inputs using sensors, or they could get inputs from other microcontrollers that are sending outputs to them. And then the way that they control the environment in the event that you need to do any sort of control, again, it's not like with a computer screen. Instead, it would be either controlling a motor or an actuator or an LED. So even if you don't know what motors and actuators are, at least you know what LEDs are. We have LEDs on phones and lots of other things. So the control could be via LEDs. So flashing an LED in a certain pattern could tell you what's going on. You have buzzers, they're just like speakers, or they could control other microcontrollers. Now, microcontrollers themselves are usually bare metal. And what that means is that there's no operating system on a microcontroller. Now, the benefit of an operating system is that it introduces a layer of abstraction from the hardware. And that layer of abstraction is what libraries typically sit on. So when you write your applications in the context of an operating system, what happens is that you have libraries you interact with. Those libraries take advantage of operating system capabilities. And so you don't think too much about it. Typically what you would find, let's say you go to download a browser, is they just say, are you running on Windows, or are you running on Linux, or are you running on Mac? That's usually just the question. If you choose Mac, for instance, in the past, it was just, what version of Mac are you running? But now it might be, are you running Mac on Intel or Mac on ARM, right? Or is it Mac on an M1 chip or an M2 chip, or is it Mac on Intel? But usually that's all they need to know, because the operating system itself handles that hardware abstraction. And how you think about it is, if you look at a phone, for example, you don't have one Android for all devices. There's one Android for every single phone that you have out there. The same thing with iOS. So if you use an iPhone, it's not one iOS for all hardware. There's usually a version for every single device that they released in the past. And that's why sometimes you have device dropped for certain devices that are older than a certain age. So that's what the operating system does. It abstracts all of that. But when you deal with microcontrollers, there's no operating system. What that means is you need to know the very specific hardware that you're programming for, and you need to know all the features of that hardware. Now, these microcontrollers are available as development boards. And one example of that is the Arduino Nicla Vision. And another example is the Sony's Presence. And on the screen, I have the Arduino Nicla Vision. It's both a microcontroller, but with certain things added. There's a camera on it. There's an inertial measurement unit on it, and it has a distance sensor. And if you look at this part, bottom right, there's a circular metal thing, and that's an antenna connector. And then to the left and to the right, all of those gold pins, those are your general purpose input-output pins that will let you connect things like sensors for input, or actuators, LEDs, and all sorts of things for output. So we all know what machine learning is, but what does it take to create a machine learning model and deploy it onto a microcontroller? The first part of what you need to do is the same as training machine learning models for normal use. The very first thing that you have to do is your data collection, obviously. But there's one difference here. So while on desktops, you could use data from anywhere, with embedded systems, you typically will want to capture your data with the same sensor that you're going to be using for inference. So what that means is if you want a vision model, then the camera that you're going to use in the wild is typically the same camera that you want to use for your data collection. So in this case, you'll want to use the camera on the collar for that. Then the next thing is you have to train a model, but there's one difference again. You don't want to go take ImageNet or VGGNet and do transfer learning with that, because if you've ever worked with phones, and phones are slightly constrained devices, you can't deploy VGGNet and ImageNet to phones. They just won't fit. So you have the same constraint, but a greater level of constraint with embedded systems. So you're going to have to take a constrained model, something like mobile nets, for example. You're still going to use your TensorFlow. If you want to do transfer learning with the constrained device, that's fine. If you want to define your model from scratch, that's also fine. But then you have to train a mobile optimized model and then fine tune it. And then when you train with TensorFlow, what you get is a proto buffer. But when you deploy to phones, you have to use TF-Lite to convert your model to a flat buffer. But that is not enough to deploy to an embedded system, because even that flat buffer relies on an operating system and TensorFlow Lite to be available. But you don't have any of those. So you have to convert to a C++ class. It's still a flat buffer, but now you use something else called TensorFlow Lite for microcontrollers to get to that point. And so at this point, you're then ready to move over to your embedded system for deployment and for inference. For deployment, you're going to write code in typically C or C++. You're going to embed that class in there. And then there's a TensorFlow Lite for microcontrollers library that you can then use that helps with things like loading up your TensorFlow Lite for microcontrollers class and performing inference. Now, recall that really what you have, whether it's a proto buffer, whether it's a flat buffer, or whether it's a C++ file, is that with machine learning inference, it's really a bunch of computations, right? So the only difference here is that you don't want to be doing computations that are not optimized, right? So you want computations that can be parallel if possible. Now, on your device, once you've got all of that, then your embedded program is going to be running in a loop. And in that loop, in the case of a vision model, what it's going to be doing is it's going to be capturing an image, and then it's going to be pre-processing the image, and then it's going to be running inference on that. And so, depending on what you train the model to do, if you train it to just look out for a human with a gun, for example, then when it finds a human with a gun in the image, it can then send out a notification. And that notification would then be via that long-range, low-power method that we mentioned earlier on in one of the slides. Of course, it could go over GSM as well. But that's your process on the embedded system. Now, if all of this sounds a bit complicated, it's because it actually is a bit complicated. But if you recall, even with regular machine learning, we tend to use a bunch of tools. While you might use something like Google Colab to experiment and rapidly prototype your model, there usually is an entire pipeline, because even with standard ML, you have your data collection and annotation and cleaning. And then how do you build a pipeline for continuous training and deployment. How do you evaluate your model on a continuous basis, detect drift, and all sorts of things. So I'm going to be talking about a platform called Edge Impulse, and Edge Impulse simply just simplifies your machine learning process, but for edge devices. And so if you go to Edge Impulse, you have a dashboard. On that dashboard, it lets you do a bunch of things. It lets you do data acquisition. It lets you design an impulse. The impulse is really just the pipeline. And then it lets you do deployment as well. When you need to get your data in, you might need to connect a device to get the data in, and Edge Impulse will let you do that. You can either connect a development board, so something like the NICLA vision that I showed earlier, but there are a bunch of boards that are supported, and you'll see some of those further down the road. You can also use your mobile device, and this is particularly useful for rapid prototyping when you're trying to even figure out whether an idea that you have is possible before you start looking for development boards. You can rapidly prototype with a mobile device. You could do data capture with your computer. And then there's something else called a data forwarder. So further down, it gets maybe more device centric, but you can also upload data. So you might have used a separate process to capture your data, whether images, sound, accelerometer data, whatever. You might want to then upload that from storage. And moving on, you're also able to connect to cloud storage buckets, because that's a very popular location for storing ML data. So you could connect to a cloud storage bucket, but once you're done, you're then able to go ahead and design your impulse. And the impulse is simply just a series of steps within the pipeline. And the example that we have on the screen is for computer vision. First of all, you have your input. So if you think about, let's say, your Keras model or your TensorFlow model, you'll have your input as an image. And you might want to carry out some pre-processing, and that's what the red image data is handling for you. It will scale your image up or down to the required size, and it will also crop the image depending on what you tell it to do. And then there's a second step there, that white image. And while it looks like it's not doing anything, it's actually doing something called digital signal processing. And digital signal processing is something you get used to with deep learning. If you're dealing with speech models, for instance, then you have to do a bunch of stuff. You can't just take speech data and throw it into a model. And then the purple block carries out your classification. That's actually your ML model. And you see it says classification and it says Keras. And so you're going to have a model there, and we're going to see all of these details moving forward. So the first thing is the digital signal processing block. In this block, you're able to look at your training data, so it'll actually render the images that you have in there. And then there's also a feature generation step, and that feature generation step takes your data and outputs something. So notice, for instance, that we have like color depth, and here we're using RGB. But if you're going to be working with monochrome cameras, and monochrome cameras are popular out in the wild, you can set your RGB depth to just monochrome. So that way it eliminates all of the color channels that you have. Now, something that is particularly important with embedded systems is the question of how long does it take for something to run? So in this DSP block, there's a mathematical operation, and it's benchmarked against a certain type of processor. So when you start to deal with embedded systems, the processors are important. but also the memory is important. And what we see at the bottom of the screen, bottom right, we have two things in a block called on-device performance. We've got a processing time, and we see that it's 7 milliseconds. We've also got a peak RAM utilization, and we see that it's 4 kilobytes. Both of these are important to note for your embedded system, because if you exceed the available memory, then it will simply not fit, or it will crash when it's trying to run. Now, moving forward, the final block that we have is the neural network block itself. And you can see here, if you're conversant with writing Keras, that this is simply Keras. At the very top, you have your import from TensorFlow and a bunch of things, and you have your model architecture. While this code isn't utilizing transfer learning, you can see that it has a convolution layer and a max Boolean layer, and so on and so forth, a flatten, a dropout, and a dense layer for classification. And you're able to control all of this, but within the constraints of TensorFlow Lite for microcontrollers. And what that means is that you have subsets. So the TensorFlow Lite itself is the superset, and all of the operations that are documented for TensorFlow are supported in TensorFlow, but not all operations are supported in TensorFlow Lite. So there's a subset. And there's an even smaller subset for TensorFlow Lite for microcontrollers, and you need to keep that in mind. So if you want to use a layer, you need to go and check the documentation to confirm that that is supported. So this is the model definition, and you can do all sorts of things. Of course, it's Keras. So further down, you have your training. You can specify the number of epochs. You can specify your train test split and all of those. And the training output, when you do train, will appear somewhere at the top right of your dashboard. I've scrolled past that. And, you know, ML is ML. You're always interested in your metrics, right? So there's a confusion matrix there. And for this particular model, it categorizes into a bunch of classes, and you can see the performance. Ignore the fact that accuracy is 100% and the F1 score is 1. That's because this model, if you go further down and you look at the on-device performance, this model would take 7.6 seconds to run, which might not be a particularly good idea. So before putting it into production, you probably want to review the model definition such that the output is much smaller, because there's also the peak RAM utilization, which is 365K, and the flash usage, which is 52. It all depends on the microcontroller that you're deploying on, but 7,600 milliseconds or 7.6 seconds is quite a lot of time. But on top of that, you can also see a feature explorer that tells you, it basically classifies the images based on your DSP generation and the classification that your training performed on your validation data set. There's a whole lot that you can do on that platform. You know, obviously you want to test your model versioning, because you might have different models that you train and all sorts of things. But when you're done, you're then able to move on to the final stage. And that final stage is, do you want to create a library, for example? And there are all sorts of embedded systems. So you've got things like C++ libraries or Arduino libraries. And then there are other platforms depending on what you're using. The NVIDIA logo might be familiar to a bunch of people, but there are all sorts of things in there. Now, beyond creating libraries, remember we said that if you have a C++ class, you're still going to have to write your code. And that code that you deploy to bare metal, it's actually called firmware. So on the platform, you're also able to build firmware for certain types of hardware that's officially supported on that platform. Any hardware that isn't supported here really isn't a problem. Just export your C++ or whatever library it is, and then go write your code in there. So this just makes it simpler to evaluate. And then on the screen, if you can see it clearly, on the first row, you've got one Arduino board that you might not be familiar with, and then the second one, which is the Nuclear Vision that I mentioned earlier. And then on the second line, there's another Arduino board. These are all called Arduino Pro boards. And if you look through, you might find something that you're familiar with if you've ever played around with embedded systems. But if not, no worries, you'll get there. And then at the very bottom of the screen, you see that you're also able to run your impulse directly. And that's really it. If you jump on Edge Impulse, you'll be able to apply your existing ML knowledge, train models for embedded systems. So depending on what it is that you're trying to do, maybe you can do it alone. Maybe you need to buddy up with an embedded systems engineer who will get you the training data that you need. You'll specify what you need, but they'll be responsible for writing the code that runs on the bare metal. And then when you're done with your model, they'll also be responsible for deploying the model. It's kind of how you might work with a mobile software engineer, right? Where you're training the models and then they're responsible for writing either the Android code or the iOS code that finally gets deployed to your device. And that's it. There are quite a few things that you could learn about TinyML. I didn't put the TensorFlow link, but yeah, check out TensorFlow Lite for microcontrollers. Check out ARM. ARM is the company that designs the chips that goes on both your phones and some computers, but also a lot of the microcontrollers that support machine learning on edge devices. Check out TinyML Foundation, check out Edge Impulse as well. And then there are some courses. There's a tiny machine learning course on edX. It's not a course, it's a specialization, 3 courses. And then Edge Impulse has 2 courses on Coursera that will get you flying through the door. And that's it. Thank you for listening, and I'm happy to take questions. Thank you. So I can't hear anything from your end. I hope it's not me. If you're speaking and I can't hear you, then please just type into the chat.
I'm sorry, I was muted.
Okay.
As I was saying, thank you very much for your talk and also for accepting our invitation. I have a question. Imagine if I want to do federated learning, where I have one Arduino board that is doing that I want to deploy a part of the model or the base model, and I want to deploy to maybe 20 edge devices, and each of them want to then perform machine learning and send back insights. Have you ever done something like that? And is it possible to also kind of simulate that using the platform that you have just shown us now?
Okay, so I heard 2 questions. The first one is about federated learning. And then the second one is emulating the devices that I talked about. Is that correct?
Yes, correct.
Okay. Okay, so federated learning is usually more focused on more powerful devices. So things like phones, for instance, they have phones are anywhere between 20 times to 50 times more powerful than some of these embedded devices that we're talking about. You think about it from the perspective of the fact that even if you leave a phone running and not doing anything, at best after 48 hours, you're going to need to charge up that phone again. So they have very powerful processors. They're energy hungry. And so for that reason, you're able to try things like federated learning, which is where the device is doing what it does, but then you're also collecting data and then you're retraining models, or you're anonymizing and sending that data back. But for edge devices, we're not there yet. In fact, we're still struggling with quite a few things that you would consider to be elementary on a phone. In terms of emulating hardware devices, interestingly, yes. Well, it wasn't an IoT session, so I didn't mention that. But there's something called ARM virtual hardware that you can look up, and it's available. It's available on AWS, it's available on Oracle Cloud. I do believe that it will be getting to Azure very soon. So ARM virtual hardware lets you emulate a number of embedded systems all the way up to the Raspberry Pi 4. There are a few differences between the Raspberry Pi 4 on the cloud and the physical one, and that boils right down to the very specific instruction set architecture that is implemented in both platforms. But yes, you're able to emulate some of these devices.
Thank you. Is there any other question from the audience? Okay, there's one here.
Thank you very much for your presentation. I just want you to elaborate what you're talking about, the advantage of microcontroller operating system. You said it introduces the layer of abstraction. I really don't understand on that one. Please elaborate.
Robert, have you heard that question?
Could you repeat the question, please?
So basically, when you were talking about the microcontrollers, you spoke about the abstraction layer that microcontrollers introduce, and the participant just wanted you to elaborate more on that.
Yeah, okay. So, sorry, I have a bit of echo. So just to be sure I got the question, but it's around the abstraction layer, right? That I mentioned.
Yes. Yes.
That is missing, yes. So typically what you get is that they don't have an operating system. So sometimes operating systems get added, but not in the sense of the operating system that you think about. So if you think of your laptop, let's take a brand new laptop that you've got. When you put it on, there's an operating system that comes on that asks you to do things. It could be Windows, it could be Linux. In fact, you can buy a Windows laptop and put Linux on it, as long as that processor is supported by that Linux operating system, right? So that's your abstraction layer. What then happens is that the operating system talks to the hardware to do things, and then the software just tells it what it wants to do. So a very simple example is in any programming language, when you say print, right? When you issue print as an instruction, the operating system is responsible for figuring out where to send that print to, right? You don't have to tell it whether it's printing to a terminal window, command line, because if you do JavaScript, it will print to a console in your browser, right? But if you do like Node.js, it knows that it's not running in a browser. All of that happens at that abstraction layer. But what the operating system is doing when you issue that instruction at a high level is that it converts it to machine language. And that machine language is very specific to the processor that you're running. So if you know different processors, like most people only know Intel and maybe AMD, but they both use the same architecture. So their machine language is mostly the same. But if you've read about the history of computers, there was a time when Apple ran on the PowerPC, there were Motorola processors and all of those things. Their machine language isn't the same, right? So when you deal with microcontrollers, you're actually talking to microcontrollers more or less at that level of the machine language. So you're not really saying print. For example, if you want to output something, and just to give you an example, let's use a washing machine, right? When you use a washing machine and you set a program, you tell it to wash, maybe heavy or light. Heavy or light, it tells the machine how much workload it has, like how many clothes you've put in, right? It gives it a rough idea. So heavy would tell it that it needs to fill the drum with water, and light tells it, to maybe fill it to 25% or 30% with water, right? But how does your code output that? Your code would output that by outputting either a digital electrical signal, which is a 0 or a 1, for a period of time, or it would output an analog electronic signal, right? And so that analog and electronic signal would then range between a certain value. So if, for instance, your microcontroller, and apologies, but we've gone into electronics, if your microcontroller runs at 3.3 volts, it could then output a value that is above 1.8 volts, but below 3.3 volts. So if it wants full water, it then outputs 3.3 volts. But if it wants, let's say 30% water, what it would then do is 3.3 minus 1.8, and then it will take a third of that and add that to 1.8. And then we'll output it to one pin. That pin controls the valve that lets water in. And that is what then translates into how much water is allowed into the drum. So that's the difference between an abstraction layer. With an abstraction layer, if you were programming Android, for instance, you would just say, you would call a function, and then that function would send some things to the OS. But without the abstraction layer, you are actually outputting some either discrete or variable electronic signals.
Thank you very much, Robert. Is there another question? Okay, this one here.
Thank you very much, sir. One question that just came to me. Firstly, you mentioned that in terms of TinyML or machine learning, it's taking place mostly in parks where you sort of like have collars on animals, and that's sort of like, those are the sensors, and you're supposed to process these things with the sensors, the actuators, to get all this information from the data set. But I wanted to find out, what does it actually take to implement this architecture, like in terms like of on the financial background? For example, let's say it was a while back, but I remember I saw that in Egypt, for example, they were implementing what is called edge agriculture. So the whole point was, you sort of like have sensors on crops, and the sensors, are supposed to tell you what does the plant need, for example. So it tells you what does the plant need. So at the end of the day, you end up having like drones which come to each plant. So like what does that individual plant need, as a way to sort of like not waste and to be efficient, with nutrients and what is basically needed for those plants. So I just wanted to find out, like, if you needed to implement something like that, what would it take, just in terms of manpower and also like the cost and whatnot?
Yeah, Robert?
Yeah. Yes, I got that. Yeah. So an example of like agriculture in Egypt, right? And so that you would call that precision agriculture. So I will start with the last question, which is how much would it cost? So it's not possible to answer immediately how much it would cost, because it depends on all of the sensors that you're using. So typically you would prototype the solution, and then if it's accepted, you would then take all of that cost. Now, I've had an argument with someone in the past who said, hey, you should still be able to estimate cost. Now, you can theoretically estimate cost because you know the various components that work together. So for example, if your plants are in a greenhouse, the question is, what are the inputs that you need to capture, right? Do you need to capture temperature? Do you need to capture humidity? Do you need to capture soil moisture level, right? Are those the only three things that you need to capture? If those are the only three things that you need to capture, then you can get an estimate of pricing for these sensors, because all of these ones now, of course, it's not only one sensor. There's a soil moisture sensor, and it's not only one sensor. There is a temperature and humidity sensor. There are different sensors for that. But then, you can say that it's going to range between, there's a sensor A that costs X amount, and there's a sensor B that costs Y amount. So either one of those, this is what our cost would look like, right? So that's talking about cost. The rest of it, of course, is in terms of data collection, if you're talking about training the model. So one of the things that I want you to know is that if you look at just an ML model, traditionally, you've always had your input layer and your output layer, right? Now, with traditional ML, because we know that the input to a machine learning model has to be numeric, right? If you're dealing with tabular data, it's usually very straightforward. You have columns of data that, if it's numeric, you hold it as numeric, whether integer or floating point. If it's text, you either use an embedding or you use bucketization, right? Whatever, but you can convert things to numeric values. And so your ML model always consumes numeric inputs. Now, your numeric inputs now will come from your sensors. That's the only difference, right? So there's a little bit of saying we're going from sensor, how do we read the sensor? How do we get the numeric values? And then how do we pass it for inference? Because remember, on the edge, the only thing you're doing is inference, right? But your input for the inference must reflect the input for training. And if you carry out any pre-processing along the way, it also must be reflected, right? But that's really it. So inputs, and then ML model, and then inference, and then your output. So in the case of the greenhouse, your output again would be via communications, right? Which is, you might want to, on the microcontroller, you could, for instance, connect to something like Twilio and send out an SMS, that says plant A needs watering, for instance, or plant A needs more sodium in the soil or more urea, whatever it is that you're dealing with. But that's the flow. Please let me know whether I answered sufficiently or if I need to dig deeper. Okay.
Thank you. It seems like you've answered sufficiently. And I think I just have one last one. Because, because of GDPR, for instance, in Europe, a lot of companies are now thinking about doing on-device computation, such as prediction, because they don't want to send data to the central server. So when we think about the fact that, most of these edge devices are very, very constrained in terms of the computational and also in terms of the capacity. How light should a model be so that it can efficiently work on some of these tiny ML devices?
Okay, what was the last part of your question? What does the model
how lightweight should the model be for it to work on these tiny or this constrained environment?
Okay, so that's a good question. It boils right down to bias variance trade-off, right? So what it means is we have a lot of things to talk about in the machine learning space. Obviously, I didn't talk about like ethical AI here, but it's still machine learning, and that's one of the things that you need to note. It's still machine learning. Ethical AI factors in then your bias variance trade-off. So you can train a model, and then the question is, does it meet your accuracy requirements, right? The confusion matrix, is it what you want? The F1 score, is it what you want? Then you then go and look at the performance and say, okay, how about this performance? Will it fit on the model, on the embedded device? Now, it depends on the device that you have. So there are benchmarks, for instance, what I showed in my slides, it's actually meant for a single processor device running a Cortex M4F, for example. But the Nikla Vision is a dual processor device that has an M4 and an M7. So what that means is, if you deployed it on that and you tested it, it might actually perform much faster than what we're seeing. And so if it performs fast enough and it fits, then you're fine. You don't need to shrink it any further. But if it doesn't, then you might need to shrink further, right? And in shrinking further, there are approaches. So do you make the model simpler? Do you eliminate some layers? Or do you carry out something called quantization? And we have both pre-training quantization and post-training quantization. But essentially that is saying, let's either drop the number of precision points in our floating point numbers. So those are the weights. Or do we even move them over from floating points to integer for storage, right? And then during inference, we know what we need to do to get back as much of the accuracy as possible. So there are techniques for answering that once that arises.
Thank you very much. Thank you very much, Robert, for that. It was amazing having you. Another round of applause, please.
Thank you very much for having me, and enjoy the rest of your day.
Okay, thank you. Okay, we have reached the end of the first part of our day. So we're now going to lunch. Then after that, we get into teams, and then we start looking at the problems.